In case of a liquid drop, due to surface tension, the molecules lying on its surface will experience a resultant force, which is acting inwards, perpendicular to the surface. In spite of the inward resultant force, the size of the liquid drop cannot reduce to zero due to the force of surface tension. It infers that the pressure inside the liquid drop must be greater than the pressure outside it. The excess pressure created inside the liquid drop will provide a force that is acting outwards, perpendicular to the surface to counterbalance the inward resultant force. Thus, the liquid drop is in equilibrium. In this state of equilibrium, there is a very small increase in the radius of the drop due to the excessive pressure. Thus, the work done is equal to product of excess pressure multiplied by area and increase in radius. The change in size of the liquid drop increases potential energy. Thus, the increase in potential energy is at the cost of work done by the excess pressure. Similarly, in case of a soap bubble, it has two free surfaces, one outside the bubble and the other inside the bubble, where soap solution and air are in contact. Thus, the effective increase in surface area is more. Hence, the increase in potential energy is at the cost of work done by the excess pressure is double than that of drop. In case of an air bubble inside the liquid, it has single free surface. So, the excess pressure inside the air bubble is same as of the liquid drop. If the bubble is inside the liquid, density of liquid is equal to ρ at some depth h, then its excess pressure is given by this relation.